So Tara Strand, who is the program leader for our Urban Battlefield Toolkit program, has asked me to give you a very brief overview of our program that's been running for the last 3 years, and then I will move into my area of cyborg surveillance. So I guess, what is the urban battlefield? The urban environment is very complex. There is social dimensions to think about, host plant distributions to think about, and very complex aviation issues if you have pest incursion within an urban environment. Managing biosecurity risk is very high priority for New Zealand, as we all realise. The risk of damaging insect pests and pathogens into New Zealand are increasing, and eradication operations in urban environments are very constrained now by public concerns and environmental issues. As we probably all remember the white spotted tussock moth of 1996 and that very large plane that flew over Auckland. So broadcast aerial pesticide applications, they may be effective, but they're also less socially acceptable. So locating the source of your pest incursion takes time, and delays increase the likelihood of spread that may then move further out of the urban environment into our forests and productive lands. Our Urban Toolkit program was guided by a program steering committee from its outset. End users for pest eradication tools were embedded within our program, providing governance and guidance along the way to make fit-for-purpose tools, developing protocols to work for the likes of MPI, and also integrating program partners with in-depth knowledge in different communities and Maori partnerships. So as I said, 3-year program, rather short amount of time to get through a rather large amount of research. We had 3 research areas. Firstly, active surveillance technologies, so being able to speed up the response and quick detection of any insect incursion or pest incursion. Split into cyborg surveillance and then alternatively an active sensor. Secondly, focusing on targeted eradication tools, so diversifying our current eradication toolkit with the likes of helicopter spot spraying, UAV spraying, and pesticide or non-pesticide strategies that could be implemented within the toolkit. And then finally was our social aspect of improving our risk communication and engagement into the community, maintaining the social licence to operate, engaging with different agencies, and also then the Maori Biosecurity Network. So briefly, highlights for you. Big one here, helicopter spot spraying. A really innovative new boom design developed within collaboration with Heli Resources, and a protocol was submitted to MPI and adopted into the brown mum ray distinct bug response plan. UAV wake modelling, so wake modelling characterised from UAVs was put together with collaborations from the US, and we realise now that it is modelling aerosol droplets from the UAV wake. This is a world first, and as you can see, shows quite a plate of spaghetti, as Tara likes to call it. So over the 3 years, our different groups have managed to conduct 70 UAV spray trials, a very large number over a very short period of time. So building up a really good protocol for use by MPI for eradication, and just being able to use UAVs within that pest eradication environment. Great highlight here, Brian Richardson and team got the ASABE Superior Paper Award in 2018. It was very, very good for their influence of young radiata canopies for aerial spray drift. And on the social front, one of our groups has co-developed with MPI a rubric for improving the performance of community engagement. So again, keeping a social license to operate, and engaging again with the Maori Biosecurity Network, strengthening iwi participation in biosecurity throughout the whole program. And a final highlight here is around developing a world-first method, quantifying host plant removal. So it's now available for use. Our model simulated eradications using host plant removal, fragmentation, and pesticide application. Initially, we used the model with gypsy moth, so a defoliator that's well known around the world, but it can be adapted to other different species, and then also has been backed up with field trials. So, my area of expertise, thank you for hanging in there, is cyborg surveillance. So, our program has worked in this area of integrating insect cyborgs into the pest management area. So, why cyborg surveillance? Speed's crucial at an incursion event. Time is money, as we all know. And the faster you can get onto something, the less money you spend, and therefore the smaller an issue may be, and then you keep your social issues at a very small scale, and you manage to keep everybody happy in the long run. And we don't see too many more large aeroplanes flying over Auckland. Currently, our response in New Zealand to an incursion is via trapping, putting out pheromone traps to trap insects, and this takes time. It also takes a very large effort. Traps are static. They also can be slightly overstated in how sensitive they can be, and then the insect has to come to you, again taking time. So we took these thoughts and moved forward and thought, well, if we could develop an insect and machine combination, we could find our insect incursion that way. So we're no longer static. We can move towards that incursion. So we're looking for the insect. We don't always need to know the pheromone that way. And hopefully we could use this with a wide range of insects. Part of the program also needed to think about parallel development with insect tracking algorithms. So understanding how a male insect would find a female insect. How does it follow the plume of pheromone from one place to another to be able to get to that female? And we've done a little bit of review on that. I'm not going to go into too much detail about it, but there is a lot of information out there about how insects find each other. So, very briefly, principles of a cyborg. I'm not going to go too far into it. Insects that use smell more strongly will have slightly more developed antennae. Within those antennae, there are tiny hairs. The hairs, called sensillum, will have pores in them, and those pores bind odour molecules out in the atmosphere. Once they find something that they like, the nerve or the dendrite that's running down the hair will send an electrical signal to the odour receptor neuron, telling the insect it has smelt something that it likes. So there is an electrical response there. And for us, this means the principle of our cyborg is to use the insect's antennae in a process called an electroantennogram, or an EAG, where you measure the voltage coming off that electrical response. So insect antennae come in huge variety of sizes and shapes. The thing they have in common are those sensilla, the tiny hairs. They will develop slightly differently depending on how strongly the insect uses pheromone as a communication tool. Like this fellow here, which is the gypsy moth. It uses pheromone very strongly as a communication tool. So, our journey. So the last 3 years, we have been developing an insect cyborg, as some of you would have seen last night. We started off with a student project, and they looked at a lot of the research that had happened and helped us move towards where we are today. Along the way, we decided we probably needed to bring in some professionals, and we employed a company in Christchurch called Infact to do our engineering design, take our ideas and move them forward a lot more quickly. So they developed version 2 for us, which we have managed to put on a UAV supplied by Eradication, as you can see in the picture. It was considered lightweight at the time. It's 1.3 kgs, which is pretty good. We had a large breakthrough. We managed to connect 2 antennae of an insect, so general electroantennagrams will only ever use 1 antennae, so you have 1 point of reference as to whether or not you have found pheromone. We're now getting 2 data streams from that insect, 2 points that we can try to confirm that we've found some pheromone. We then did a little bit more development, worked through some kinks, and by the powers of 3D printing, we've come up with a very lightweight, very fast, compact design for a insect cyborg or mobile EAG. Along the way, we've also realised that we had to look at the data stream coming from our insect. The insect is thinking a lot faster than we can possibly measure, so we've managed to increase our sampling rate and double it to a really fast number, so 1 kilohertz, if that means anything to anybody. And just with integrating some really nice hardware into this. There's still places we can go with this, but at the moment we have a nice prototype that we can test in the lab and in the field. So our approach to validating this nice version 3 cyborg was we used a common New Zealand pest, light brown apple moth. The reason we went this direction is we knew we could breed them, we knew we could get them, and in New Zealand they're everywhere. With the help of Planted Food Research, we couldn't have done it without them. They have a colony in Auckland and they supplied pupae to us, so we didn't have to continually run a colony. I'm not going to delve too far into exactly how we validated this. We did a process called dose response testing. We looked at how much pheromone we could sense from our insect, compared it between a state-of-the-art laboratory setup, and looked at how small a microgram of pheromone we could get down to and still see a response from our insect. And then hopefully proceed that on to testing out our cyborg. So very quickly, I'm going the wrong direction. We compared the cyborg to our lab machine. Look, the main take-home message here is the trend is the same. Light brown apple moth is not very sensitive, so we do have to take this with a slight grain of salt. The way we dealt with this is we moved forward. We sent my colleague Brooke O'Connor there on the left off to France and Canada to work with world-leading electrophysiologists. They validated our cyborg with a very wide range of species, and they've collected a very large amount of data. The species that we're working with are sort of reasonably well known in the entomology space. Agrostis ypsilon is something that the French work with a lot. It's like our light brown apple moth. It's something they can breed easy. There's a lot of data to compare against. In Canada, we're working with gypsy moths, so really being able to build a database, a library to be able to say we can use the cyborg with a high-level pest that we could end up with in New Zealand. And spruce budworm was just a nice side event of Canada. They happened to have a colony there. We could work with it. Big take-home message is what you have seen from last night is gypsy moth. Gypsy moth, you will notice that there is a lot of zeros at our very left-hand point and right down here. So that is 1 picogram of pheromone. So it is a very highly sensitive species, and we can pick up very low doses of pheromone with the cyborg, which was a great accomplishment for this program. To be able to back all of this lab work up, the Canadians use glass houses to be able to look at active space around their traps for the gypsy moth trapping programs. So Brooke would walk around past the gypsy moth trap and see if she could pick up the pheromone coming from the surveillance trap. It turned out the glass house wasn't big enough, so she was standing 30 metres away and she was still picking up pheromone. And because of the situation they were working in, she couldn't take the insects outside of the glass house to be able to test this. So this is something we would love to go back and do. and work with the Canadians. They're very keen to do more work, look at the active space around these monitoring traps to really know how far they're drawing these insects in. During all our development, we've tried to stay very species agnostic. We don't want to focus solely on a moth. We don't know what's going to come into this country. So this here is the Asian longhorn beetle, a very large, rather aggressive beetle from what I'm told. Tried to bite Brooke quite a lot as she was putting him into the foam. We couldn't hook him up in this setting, but we can work with different size insects, and with minor tweaks to our prototype we can make it slightly bigger to fit. I've also had queries, could we use this for other species? Could we use this for brown marmorated stink bug, for example? And I don't see why we can't try it out. They do use pheromone as communication tools, communication device, so we can give it a go, we can see what happens. So in summary, we have an insect cyborg. It's the first dual antenna cyborg that is lightweight and can be put onto a UAV. We had great results with gypsy moths, which is excellent. Detection from 30 metres. Operational testing, we'd really love to get out there. This is the end of the program for us. We wrapped up in September, so we really want to move into more of an operational phase. Keeping the species agnostic approach, we've tested this out on 4 different species, but we'd very much like to keep this very wide, really fill our library with data. This also made a great splash overseas. I'm actually lucky it came home. The Canadians want to buy it, so we only have 2 at this point, and if I couldn't let them have it. So very quickly, lots of collaborators in this program. Urban Toolkit was great. We couldn't have done it without all these different groups, and we can't do it without the stakeholders, so thank you to all of you. Without the funding help from Forest Growers Levy Trust, we can't keep pushing on. Thank you.